the next topic is, for Riemann sums, is the topic of partition. Suppose you have an interval from 0 to 10. A partition of the interval is just a way to divide the interval. So for example, I can partition it like this: from 0 to 2, 2 to 3, 3 to 8, 8 to 10. And the partition would be 0, 2, 3, 8, 10. I can also say from 0 to 4, 4 to 6, 6 to 7, 7 to 8, 8 to 10. I can partition it any way I want. So this is the partition. Or I can say 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. So the partition is this. So a partition is just a way to slice up an interval. Okay, we're going to concentrate on regular partitions like 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 0 to 2, 2, 4, where the gap between these numbers will be, the gaps will be equal. And let's take a graph of a function, any function. Okay, that'll be f of x. Suppose the function looks like this, and we want to calculate the area or measure the area under the graph. So one way to do it is to slice up. Let's say I wanted the area under the graph between A, which is this number here, and B, which is this number here. So I can slice up this interval here from A to B, partition it. But I'm going to use a regular partition where these gaps between numbers will be equal. So the width, so what I'm going to do is I'm going to slice up the intervals, okay, like this. And the width of each slice, delta x, will be equal. So if this slice here is delta x2 and this is delta x3, these widths will be equal. So for example, if the interval is from 0 to 10, I can make it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And this is what the area looks like after you slice it. So the area under the graph looks like this. Okay. I partitioned it. Now, to calculate the total area or to measure it, we need to calculate each of these areas of each of these slices. Let's call this area 1, and this area 2, area 3, area 4, area 5, etc. Calculate the area of each of these slices, add up all of those areas, and that'll give you the total area under the graph. Take this function, and this can be anything. It looks like an increasing function. This is x, and this is y. If I wanted to measure the area under the graph, I can slice it up, and I'll show this in the next graph. Here it is. I can slice up the interval, and then the areas of these slices are not rectangular. We'll try to make them as rectangular as possible. Okay, the width of each of these slices is delta x with a subscript. So it could be delta x1, delta x2, delta x0, etc. So one way to approximate the area is, we already know the width. Now we need to figure out the height. So draw rectangles like this, where the height of the rectangle is the lowest point in that part of the graph. So for example, when you're in this part, you draw a rectangle like this. From here to here, the rectangle will be like this. Okay, and then here the rectangle is this one, etc. Okay, the area of each of these rectangles would be width, which is delta x, times the height, and then the height is f of x. So it could be f of this x or f of this x. So for this particular slice here, the height is f of x of this x. Whatever this x is, f of x is the height. For the next slice, it's f of x for this one. Okay. Or we could also draw rectangles by picking the highest point in the rectangle. So for example, if you're finding the area of this slice, you draw a rectangle that goes as high as the highest point of that region. So like this. For the next slice, the height of the rectangle is not there, but it's there. And then for the next slice, it's like this. Okay, here's what happens. The area should be under this black curve. But if you use these blue rectangles, the area will be a lower area. It'll be underestimated. So we'll call it SL, lower sum. If we use the red rectangles, the area will be overestimated by these little bits. So you're counting these, but they're not part of the area. So we'll call it SU, S upper. So for S lower, we use the lowest point of the rectangle of the curve. And then for the upper area, for SU, we use the highest one. So for example, for this one, the red rectangle will look like this. Okay. And if we do the area of each rectangle, okay, let's go back to the blue graph. The area of this rectangle will be delta x0 times f of x0. Delta x1 times f of x1. Delta x2 times f of x2. Delta x3 times f of x3, etc. And here's what the sum will look like. The lower sum will be f of x0 times delta x0 plus f of x1 times delta x1 plus f of x2 times delta x2, etc. How many of these do we have? N rectangles. So we could write it as a summation from 1 to n of f of x I minus 1 delta x I minus 1. Why is that? First I is 1, 1 minus 1 is 0, so that's x0. We have f of x0 times delta x0. All this means f of x0 delta x0 is this area here. It's this area. I'll use a different color. F of x1 delta x1 is this area, etc. So this is called the lower sum. Now if you look at the graph with the red rectangles, the red rectangles, for the red rectangles, we don't use f of x0, we use f of x1 for the first rectangle. So it'll be f of x1 times delta x1 plus f of x2 times delta x2. It's just a matter of where you start and where you end. It'll still be summation from 1 to n, but this time it'll be f of xi. Our first f is f of x1 times delta x1, which is this area. F of x2 delta x2 is this area. F of x3 delta x3 is this area, etc. Okay. The star means we're assuming that the function is increasing. Why is that? Okay, if the function is not increasing, only if the function does this, and then it comes back, watch out. When you're doing a rectangle here, the lowest point is here, the highest point is here. But when you're on this side, the lowest point is this one and the highest point is this one. So the higher x is, the statement, the higher the value of x, the larger the value of y, only applies when the function is strictly increasing. So be careful. So if you're doing a rectangle here, it'll be like this, but here it'll be like this, and then the next rectangle will be like this if you're doing the lower sums. So this is why I have a star here. We're assuming that the function is increasing. So it's higher at x1 than it is at x0. It's higher at x2 than it is at x1. It's higher at x3 than it is at x2, etc. Let's do some examples. First example I want to do is this. Take this function here f of x equals x squared plus 1, and in the interval 0 to 4, it's an increasing function. I want you to divide the interval by 4 into 4 slices and then calculate this sum here. So here's the sum. The lower sum is summation of 1 to 4 f of xi minus 1 delta xi minus 1. So it'll be f of, first I is 1, 1 minus 1 is 0, so it's f of x0 delta x0. Second I is 2, 2 minus 1 is 1, f of x1 delta x1 plus f of x2 delta x2 plus f of x3 delta x3. Okay, f of x0, okay, x0 is 0. The partition is like this: 0, 1, 2, 3, 4. x0, x1, I'll write them: x1, x2, x3, x4. So it'll be 0 squared plus 1 times 1 plus 1 squared plus 1 times 1. Why 1? Because delta x is the gap: 1 minus 0, 2 minus 1, 3 minus 2, 4 minus 3. Delta x is equal to 1. 1 squared plus 1 times 1, etc. When you calculate this, you get 18. For the upper sum starts at xi, and I is 1. So it'll be, first number is f of x1 times delta x1 plus f of x2 delta x2 plus f of x3 delta x3 plus f of x4 delta x4. F of x1, so it'll be x squared plus 1. That's 1 squared plus 1 times 1 plus 2 squared plus 1 times 1 plus 3 squared plus 1 times 1 plus 4 squared plus 1 times 1. When you add all of this up, you end up with 34. This is the lower sum, and this is the upper sum. Okay, they are lower sums and upper sums of what? Of this function. Okay, here's another example. This is a good one. F of x equals x cubed minus 2 from 3 to 9. So x0 would be 3, x1 would be 4, x2 would be 5, x3 would be 6, x4 would be 7, x5 would be 8, and x6 would be 9. How many intervals do we have? 6. 9 minus 3 is 6. And we are assuming that the gap between the intervals is 1. So the lower sum is summation from I equals 1 to 6, but it's xi minus 1. So you start with x0. So it'll be f of x0 delta x0 plus f of x1 delta x1, etc. all the way to f of x5 delta x5. Why? Because 0, 1, 2, 3, 4, 5 will give you 6 numbers, 6 intervals. F of x0, x0 is 3, so it's f of 3 times, I'm just going to write 1 for delta x, plus f of 4 times 1, plus f of 5 times 1, plus f of 6 times 1, plus f of 7 times 1, plus f of 8 times 1. So that'll be 3 cubed minus 2, plus 4 cubed minus 2, plus 5 cubed minus 2, plus 6 cubed minus 2, plus 7 cubed minus 2, plus 8 cubed minus 2, which ends up being 1275. For the upper sum, it's summation of f of xi delta xi, I equals 1 to 6. So this time we start with f of x, I equals 1, so x1. I equals 2, that's x2. I equals 3, x3. Delta x is equal to 1. Delta xi are all equal to 1. So it will be f of x1 times 1 plus f of x2 times 1, etc. And remember, x1 was 4. Here it is. x1 was 4. Okay. So it will be f of 4 times 1 plus f of 5 times 1 plus f of 6 times 1, etc. F of 4 is 4 cubed minus 2, because the function was x cubed minus 2. F of 5 is 5 cubed minus 2, etc. And this ends up being 1977. Well, neither, in the previous example, neither the 18 or the 34 approximated the area well. In the other example, we got 1275 for the lower sum and 1977. That's a big gap. So how do we make sure the gap is smaller? How do we get accurate results? By taking more of these, by partitioning the interval, by increasing the value of n. So you have more slices. For example, if you use 1000 slices, you'll get a much better value for both SU and SL. How do we make sure we get a really good value of the area? And the answer is, here's a regular sum. I took one of them at random. By making n tend to infinity. So if you take the limit of all of this, as n tends to infinity, this limit here is called the integral of f of x with respect to x between a and b. Okay, and dx stands for with respect to x. So the more of these slices you take, the better the result is. But the best result is obtained when you take an infinite number of slices. Why? Because you're not going to leave any gaps in the graph. I'm going to get a graph to show the gaps. Here's one. If you use the lower limit, you're underestimating the areas by these little triangular looking areas. The total area minus these triangular looking areas. They're not triangles. If you use the upper sum, you're overestimating the area. Even if you use the middle number, you still don't get an exact value for the area. And the only way to get it is to use an infinite number of slices, but that's an integral. That's called a definite integral. Okay, so this is when n is infinity, this is called a definite integral.